Hello, this is an extra video on a topic that is tangential to what we will be covering during this course. And it's something that I'm personally interested in, so I thought it would be interesting to give you a feeling about the relationship between eigenvalues and resonances. So we have seen, you have seen in linear algebra what eigenvalues are when you're talking about matrices. We have seen resonances in the case of the spring when forcing terms make the spring explode, or the oscillations keep increasing over time. And now I'll try to give you a relationship between these two topics that might seem really far away. It's going to be a different video than usual in the sense that I am not going to be building the mathematical background needed to actually solve problems, but I just want to give you a feeling about them. So let's look at eigenvalues first. So A is a square matrix, X is a vector, and we want to solve the problem AX equals lambda X. This is called an eigenvalue problem, and lambda is an eigenvalue. We know that eigenvectors and eigenvalues are, in certain sense, a property of the matrix A. So if we change the matrix A, we're changing the eigenvalues and the eigenvectors. What happens if A is actually not a matrix? I'm not going to be precise in stating exactly what A is. Later on I will be saying that A is an operator. But let's start with the idea that A is just not a matrix. And we have been studying ODEs for a while, so let's think about A as the derivative with respect to time. And X is not a vector anymore, is actually a scalar function of time itself. Then our eigenvalue problem goes from being a matrix problem to actually being an ODE, a kind of an odd ODE, because what we have is that we want to find both lambda and X that solves derivative of X with respect to t equals lambda times X. And this is an ODE that we know, and we know it has a solution for every lambda. The solution is xt equals e lambda t. We can do this when the linear problem that we're looking at, the problem we're looking at is linear. And then we call d over dt a linear operator. When we have a linear operator, then we can look at eigenvalue problems and try to look for a pair of lambda and X. There is a typo, it should be exponential of lambda t. When A is a linear operator, we can look for eigenvalues. And now the X that used to be an eigenvector is now called an eigenfunction because it's a function. Any linear ODE can be associated to a linear operator. Let's look at an example. I'm not going to be going in a generality, but this is a linear ODE, non-constant coefficients, non-homogeneous. The first thing we do is forget about the forcing term completely and just look at the homogeneous equation. Then we can look at it and we associate this ODE with a linear operator. Literally what we did is taking the left-hand side and cancel y from all over the place while keeping the derivatives. If we have an operator A, we say that X is in the kernel of A if AX is equal to 0. So trivially, homogeneous solutions are elements in the kernel of the operator, of the differential operator that we have substituted to our ODE. So let's try to use this view of operators and differential operators to help us understanding resonances a bit better. So let's think of A as a very broad and not very specific differential linear operator in which we know the existence of an eigenpair, so a pair of eigenvalue and eigenfunction. V in this case is a function. So we want to solve the ODE AX equals to V. So we have replaced the forcing term with the eigenfunction of the operator. Now this looks a bit like things we have seen when we were looking at linear ODE systems. When we were looking at two-dimensional linear ODE systems and we were putting elements on the eigenvector associated to the matrix, then we knew that the elements on that eigenvector were moving according to the eigenvalue. So with a bit of a stretch, we can imagine that if we're looking at this ODE, or differential linear operator applied to x, and we're putting it equal to one of its eigenfunction, we can imagine that it should work similarly to how it works for linear ODE systems. So we can expect that if lambda is positive, then whatever behavior we see in V, it's going to be amplified over time. And if lambda is negative, then whatever behavior is in V, then it's going to be decreased over time. And it's going to tend to 0. So when we have a forcing term that is an eigenfunction of our differential operator, then this creates resonances with the differential operator itself. It's gonna that forcing term can either be amplified by the differential operator or decreased and tend to 0. So we can look at operator theory, and this is the study of operators in general and in the applied sense on the eigenpairs of these operators. So it can tell us which forcing terms are going to be dampened away by the differential operator and which one are going to be expanded. So now with this background, let's look at what happened at the Tacoma Bridge. This is an amazing drawing, I did it myself, of a bridge. So we can imagine that we have this bridge with a lot of different pieces, because we have like the supports, the beams, all of this connected together. And we can imagine that we have an extremely complicated PDE that models the behavior of the bridge. So by this I mean that we have a function y in multiple coordinates and a PDE that is a function of y and all its derivatives combined in a lot of different ways, and we expect that to be equal to 0 and have no forcing term. And we expect that if everything goes well, when the solution is equal to 0, then the bridge is standing. It's not collapsing, it's not moving around, so y should be a stable solution. And then we can associate a linear operator to the PDE we just wrote. So we can create this linear operator A, and we can imagine that to be sure that our bridge is going to be standing, we can solve the problem AY equal to x, equals to 0. But then the wind came and actually added a forcing term to our homogeneous PDE. And now this forcing term actually happened to be, at least in part, composed by an eigenfunction associated with a positive eigenvalue. So that eigenfunction, placed as a forcing term, got amplified over and over by our linear differential operator A. So the oscillations that started with the wind just kept growing. Actually, in the Tacoma Bridge, it didn't keep growing that badly, but they did not get dampened away. They were quite stable. And that was the problem. How can we avoid it? How can we make it never happen again? So ideally, we can study the operator A and just check that the wind is not an eigenfunction. There's just a little problem with that. Usually, operators associated with PDEs have infinitely many eigenpairs. Actually, they always have infinitely many eigenpairs. But sometimes they can be uncountably many. Think of the very first example that we saw, dx dt equals lambda x. That has infinitely many eigenvalues that are just like the Boole real axis. So sometimes detecting eigenvalues and eigenfunctions can be a very, very hard problem. So what does that mean? That we actually cannot avoid this ever happening ever again. So much so that in 2000, the Millennium Bridge in London had the same problem. The only difference was that, while the wind was not a problem, people walking on it were enough of a disturbance. So you have to think about the fact that when you're looking at a bridge, there are many things that can be a forcing term that could be resonating with your operator. You could have wind, you could have people walking on it, you have cars passing, and each one of this has probably a different behavior and could be picked up by your differential operator and amplified. In connection to this video, I'm going to give you a couple of links. One to the Millennium Bridge, showing you how it started oscillating with people walking on it, and another one of some people trying to show you which forcing term does a bridge react to. I hope you're going to be enjoying those videos. I hope you enjoyed this video as well.